this webinar is really about get a basic idea of F1 aerodynamics. Therefore, here the idea really is again that we or you get into the role of F1 aerodynamist. So if you go on the SimScale webpage on simscale.com/F1, simulation projects, and you can just import them by clicking into your SimScale account for free, for sure, and can just run them and get the results. So the idea is start them, then you can analyze them and discuss them later on in the next webinar, on this webinar with Nick. And for sure, we also provided some resources for you, which you can find here. For example, FAQs. Here is again a quick guide how to run the simulation. I think it's very obvious, but in the case you have any questions, you can look up here. We've done the same for how to analyze the results. And on F1 Technical, there is the possibility to discuss everything. So we will also have a look at this forum, and if you have any questions you think which are important maybe for a bigger audience, just write it here and then we can have a good discussion. Maybe just we'll just show you a very fast how to create a SimScale account in the case you don't have one. You just on the SimScale website just go on sign up here, given all your details, like name, email address, and then you got a mail and you can log in the first time. Everybody who attends this course will get free computing hours so that he can run all the simulations as much as he wants. Therefore, it's very important that you also register here and that you have a SimScale account before you register here. So if you don't have a SimScale account, just send us the email if there are any problems and we will take care of it. And yes. If you're a student, by the way, you can choose a SimScale academic plan, and there you get, in general, resources like computing time for free. So just if you want to import a project, just click on the link. Then enter your login credentials here. Then the project is important. That can take some seconds. And then here you have, in this case, 3 simulations of a single F1 car, which are ready to run. So you just have to press the start button. The simulation will run, and then you get an email when the simulation is finished, and you can access the results. Great. Yes. Maybe just some general things. When the simulation is done, I will just start this one here. For sure we are prepared. There are 2 options to visualize and analyze the results. First of all, you can use our online post-processor, but in this case, because you want to really do a lot of stuff with it, we strictly recommend to download the results and do the visualization locally. Therefore, you just have to click here on download results, and then the simulation results will be downloaded to your computer. And for doing this post-processing, analyzing, there is a free software called ParaView, which you can use. And this you can all download it for free on www.paraview.org, or just click the button here and download it from SimScale. After Nick's presentation, there will be some time for question and answers. So if you have any questions, just write them in the chat, and Nick will answer them later after his presentation. Thank you very much. And now I'm very happy, yes, that Nick will drive us into the world of F1 aerodynamic. Bye.
Okay, good afternoon, everyone. I'm Nick Perrin. I want to say thank you to SimScale for organizing this workshop. I'm very glad that we have many people attending the workshop today. First of all, I hope we can make it accessible and enjoyable for you. Most importantly, it has to be fun for everyone to just get a bit more of an insight into Formula One aerodynamics and CFD, and just for us to share a bit more of what we are doing every day. Okay, so I'm going to start with a quick introduction of Formula One aerodynamics. And you probably recognize the Formula One car that I've been designing, and that is open source and that you can access, and that's been used for these simulations. And the first thing when you think about Formula One aerodynamics is to think that there is a very long and sometimes complicated set of regulations behind it all, and that we need to take this into account. As you can see on these pictures, I've put the boxes that the FIA technical regulation is telling us where we can and where we cannot design our car. And it's very clear that, you know, in many areas we are maximizing the space that we have, and in other areas we are actually designing inside the box, well inside the box. And just to give you an example, you can see that the front wing of the car is pretty close, I would say, to, you know, within 1 millimeter of the walls of the box. You can design it inside, and that shows how critical it is to maximize the size of the front wing. But for example, the nose, specifically on our car, doesn't use all the space. You know, in plan view, we could make it actually fatter, but we've decided to make it thinner for aerodynamic reasons. And you can also see that the floor of the car is using absolutely all the space available in terms of plan view size, but then the bodywork is much smaller than what you can do. And this is all using experience and testing as well. And I guess one of the main thing when you design a Formula One car is to try and understand where you should use all the space you have and where you should actually design inside the space that you have. And it's a bit of it's like a Lego bricks game, I would say. A lot of the aerodynamic functioning of the car is actually dictated by this rule book. And we will see it later, but some of the vorticity coming off the front wing, for example, is coming from the discontinuity of the box that we can design the front wing into. Some of the top speed of the car is dictated by the size of the rear wing box. So you can see that it's really tight, and that defines what a Formula One car should be these days. The other constraint that we have is that we're going to race on different racing tracks, and I've put 3 of them here. We go from a very slow track like Monaco to a sort of medium speed track, Barcelona, and a high speed track like Monza. And the main difference is that what we call required efficiency will change. This is telling which ratio between downforce and drag will work and will make the car go faster if we put it on the car. And this ratio will change if you go from Monaco to Barcelona to Monza. So the actual shape of the car is sort of dictated as well by the racing tracks we are going to. I've put some numbers here, and you can see that the ratio is about 1 for Monaco, 1.5 for Barcelona, and 3 for Monza. And this is something to keep in mind for at a later stage when we sort of develop the car. These days we develop the cars in both wind tunnel and in CFD. In the wind tunnel we can use up to 60% model car size by regulation, and the speed of the wind is maximum 50 meters per second. All wind tunnels have got moving belts, and this is critical for Formula One. And they also have this boundary layer suction system. So effectively what you want is that there is no boundary layer on the ground moving. But the air coming from the fan will hit the moving ground with a certain relative speed to start with. So there is a boundary layer created. And there is a complicated system sucking the air. So the air is really close to the ground and no relative speed with it, effectively like in the real world. When the car is moving and the ground is stationary, as well as the air around it. And the other thing is the car motion system. So effectively in the wind tunnel, the car is moving around to simulate different attitudes of ride heights and steering angle and yaw and roll angle. And it's fully now automated in wind tunnels. Now CFD has grown over the last 15 years, let's say, and it's become a major tool for us as well. We use models that have got 50 million cells or more. We check also the car attitudes. So it's not about just checking and testing the car in one specific condition, but it's about moving the car around like on a racing track and see what the aerodynamic results are. We also have obviously the moving ground, and that's obviously very easy to do. We can also add some thermal effects, so effectively in your engine bay, the temperature of the air going through the radiators or the engine, and we can add this to the CFD model to make it even more realistic. And the thing with CFD is it's such a good tool to visualize what the airflow is doing. You can't really do it in a wind tunnel, but the CFD is giving you an extra sort of layer of understanding. The other thing is the correlation is improving a lot between CFD and real world, and it's quite clear that it will become the main tool soon to design these cars. Something quite interesting when you come to design a car is to see what the challenge is. And if you compare a 2010 front wing on the Mercedes car with a 2015, it's really clear that the development rate is really fast. The front wing was pretty simple in 2010, and you had sort of two elements that were nearly two-dimensional. So you can say that the front wing itself was probably about 100 parameters in a CAD system. And 5 years later, you can see how much more complex the front wing is for the same set of regulation. You now have 6 or more elements, nearly 7 on the outboard, and probably about 1,000 parameters to design this front wing, and develop it takes much more time as well. When you're on the racing track, you've got different tools to study aerodynamics. The first one is telemetry, so you can measure push rod loads, pressure tappings, so static pressure on the floor, for example. You've got a pitot tube to give you the dynamic pressure, and then you can put a rake as well. So these people are doing it more and more, and you can see an example here. It's a very big one on the side, and that's to measure the actual total pressure in the flow around the car. So you can see the effort that is put in measuring and correlating wind tunnel and CFD with the real track. And the last thing we do, and it's quite fun, is to do the flow viz. This is really to look at the direction of the flow on the surface, and if there is any sort of problem with attachment, we can see it here. And this can be compared with CFD, we'll see later. The specific of F1 aerodynamics is the ground effect. The cars are so low. The front ride height is not more than 5 millimeter, and actually touching in a straight line, as you can see. So you have to also work on the mechanical setup of the car to make sure you control this attitude and use the ground effect to its maximum. Okay, so we're gonna try and do a live post-processing of the CFD simulation that's been done on the SimScale platform that you can download yourself on your own computer. So this is what we're going to try and post-process and achieve. And I'm going to actually close ParaView now and restart it so we can effectively look at the steps together. So you can download ParaView from the internet for free and do the same operation as what we're going to do now. So if you go open and the simulation file that you've got, first thing to do is to jump to effectively the step number 1, which is the last step of the simulation, so after 5,000 iterations. You can see that you have a number of mesh regions to select, and we're going to select everything and apply, which is going to load the model into ParaView. So that's going to take 10 or 15 seconds. So don't forget to jump to the next step, otherwise you're watching the beginning of the simulation and nothing is happening. You can see the progress bar here. I'm not going to show you everything about ParaView, but the basics to just to try and achieve this post-processing together. Okay, so the loading is finished. I think you have to click here so you can actually see it. Okay. What we see here is the actual box of the simulation, and you can see the car here. This is the complete volume and mesh used for the simulation. We don't want to. We want to only look at the car. So what we're going to do is to use a filter and extract only the car surface. The filters are a suite of tools that allow you to create certain features in the post-processing. Okay, so I'm going to go extract block, and I'm going to select only the car and the wheels, and apply. Right. So now we've got the car only. The other thing I want to do, so if you fit to screen. Okay. So now we've got the car, and it's colored by pressure. So static pressure on the skin of the car. Obviously, we're looking at only half the car because only half the car has been simulated, and we do a symmetry if we want to see the complete car. So the static pressure is here. Just going to move this. Okay. And we want to change the scale to make it a little bit more easy to understand. So what we can do is rescale to custom range. And I know that I want to look at the pressure between 1,800 plus and minus 3,600. This is effectively the speeds of the simulation is 60 meters per second. So the pressure is in ParaView is actually pressure divided by density. But in a nutshell, I want to look at the pressure coefficient. So I want to put a scale that will show me a pressure coefficient of 1 and minus 2. So 1,800 Pascal is effectively the dynamic pressure, and minus twice the dynamic pressure. Right. This is more like it. So this is what we are used to sort of look at when we develop the car. It gives a nice range of static pressure, and you can see quickly that we are going from region of suction in blue under the rear wing, and in the diffuser under the front wing, and region of overpressure, so on the top surface of the front wing, top surface of the rear wing. Obviously, the inlet here has been blocked in this simulation, so there is stagnation pressure in front of it. And you've got also pressure, in front of the tires, slowing down the car. So very quickly, you see what's happening around the car. What we want to do now is to see what's happening in the flow around the car as well. So we're going to create a slice. So we go back in filters and we select slice. And we have to define the plane that will slice effectively the domain. So I don't want to see the plane. I want it to be centered at 0, 0, 0. And it's going to be with a normal along the y-axis. Okay. Apply this. And still show the block. Okay. What I've done is I've sliced the actual car, but I didn't slice the entire domain, so I have to do it again. So I'm going to delete this, but this time I need to select the case foam and go back to the filter, slice. Okay. Apply. Okay. I don't want to see the plane. Right. That's better. You can see that the slice is colored by pressure, but I want the slice to be colored by velocity, but still have the car colored by pressure. That's fine. The car that we see comes from the extract block here, and the eye is showing that we are seeing it. But I want the slice to be colored by velocity, and that's going into U here. Now you can see that the scale is not quite right, so we're going to go back and change the scale just for the velocity. Okay. And we know that the simulation has been done at 60 meters per second, so it's quite nice to put a maximum of 60. Right. There you go. So effectively, red is 60, and it's very easy to visualize the wake of the car. So, the areas where the velocity is dropped below 60 or very, very low indeed, in blue here in this area, close to 0. If I zoom, you can see the wake inside the cockpit here. You can see that the air is effectively stopping, stagnating in front of the engine inlet that is blocked as well. And the other thing you can see is there is a huge acceleration of the flow going under the rear wing and slowing down of the flow going over the rear wing. And if I go back and color by pressure again, you can see the direct link between velocity and pressure. Effectively, under the rear wing, the pressure is lowered and is increased over the rear wing. And this is purely the Bernoulli effect that we know. So I will go back to coloring by velocity, changing the scale again. Make it look nice. Okay. That doesn't look too bad. You can very quickly move the slice around just by changing the origin. So I'm just going to move it by 0.2 of a meter in the minus direction, and the plane is going to come towards us. Here we go. So just moving the plane around, you can actually study what's happening around the car. So this is normally what we're doing. We are looking at the pressure, the static pressure on the surface of the car. That's one thing. And then we look at the velocity or the total pressure is similar in the actual flow field around the car. And using the combination of both, you should have all the information you need to understand how the car is working, how it is performing, which area of the car can be improved. And I'm going to give you a couple of examples next. The last thing I want to show you is how to create some streamlines. So I'm going to move the plane back to being in the center of the car. And again, coming back into filters and streamline tracer. You have some shortcuts here as well for certain filters that you can use. Okay, so I want the source to be a line. Okay, here we go. So we have a line now. And I want the line to be close to the front wing, so it will be easy to see what's happening. So let's define the 2 points of the lines here. So 10 centimeters above the ground plane. Okay. And I can apply that. That should effectively, here you go, create some nice streamlines. I should move it to be closer to the front wing, so effectively x minus 1 in meters. Okay. So this is giving us a good idea of effectively the direction of the flow. We can also select different options, but I'm not going to show all the options now. The last thing I want to show you is to remember the flow V's on the rear wing on the F1 car that I show you. Well, we can actually simulate the flow V's as well in ParaView and compare the pictures with what we have. So I'm going to hide this. I'm going to hide the slide and just skip this. I'm going to quickly create the symmetry so we can see the full car, which is a bit nicer. This is called reflect. Apply that. Okay, so this has to be Y max in our case. Do it again. Perfect. That's a bit nicer. That's a full car. Okay. I have to change the scale again. Didn't save it. That's okay. Rescale. I like to keep a scale sort of constant as well to what I'm used to, because this is about absolute values as well. You know, to see how a car works, I like to use always the same scale. Okay, and now we can color by surface LIC, and this will effectively show us flow V's. I just have to change an option here to make it look on the full car to wall shear stress. Here you go. It's better to zoom on the car when you use this functionality. And I'm going to look at the rear wing. And do a zoom here. And that didn't work because we are looking at the car effectively with some perspective. So I can just zoom this way. It takes a little while, so I come back to surface. I'm going to do it like this. Okay, do the zoom and do LIC again. Perfect, that's better. So what you see here is effectively the same as taking the picture on the racetrack. Here you go, with the flow vis on. And you can see that what we're after is to look at potential separation, so the flow not following the surface anymore. Actually, in this case, the flow is following very well the surface. There's no separation, maybe because it is a Red Bull rear wing, so it's going to work anyway. But you can have, and I experienced in the past, rear wings that separated, and you will see a sort of a messy bubble in places. And that's a bad sign, and you need to correct your rear wing. And in the simulation, you want to see it happening as well if it has to happen on the real track. This is one of the areas that's really difficult to correlate. But CFD getting better and better, you can effectively predict that the wing is going to separate. In this case, the wing is very clean. There's no problem with this wing. Okay, the last thing you can do when you've got some nice pictures like that is save a screenshot and quickly create the pictures that you want to save. And that's what we've done before this workshop today. We've saved a series of pictures, and I'm going to use them to go in a little bit more details about how the flow is sort of going around the car. Right, so effectively you can see the LIC here inside the field and not just on the surface of the car. And this is colored by velocity in this case. I'm going to close this one and go back to the front of the car. Okay. So I'm just scrolling through the pictures so we can effectively move along the car in the X direction. And that's the front wing that we're seeing here. And just go from the front to the back of the car and sort of have a feel for what's happening. I'm going to stop about there. And you can see quickly that you've got vorticity happening and rotational flow. And remember what I was saying at the beginning with the set of regulation, with the boxes. Effectively, the center of the rear wing, of the front wing, is just a very simple profile that doesn't generate any downforce. It's what we call a neutral profile, and this is the FIA dictating this, up to Y250, so 250 millimeter away from the center of the car. And then you can pretty much do what you want in this area. So you will effectively create a wing that generates downforce. But it means that you have a big discontinuity here that will by itself generate a big vortex. If I go a little bit further, right, I have to close it again, sorry, and open it again. Okay. If I move a bit further, you can see this vortex has been generated, and it's pretty big. And this is actually in Formula One what we call the Y250 vortex. And it's always there, purely because of the way the regulation set is written. It's not necessarily a problem, and we have to use it to our advantage. But this is something that is here from the beginning, from the very start of designing the car. On the other side of the front wing, the same is happening. Obviously, this is the end of the front wing. The air wants to rotate around and go under, just due to suction effect. So you can see that you've got a big vortex in one direction here, going this way, and outboard you've got another one going the other way. Actually, you can even see that this one is split in two vortices. You've got a small one in this sort of tunnel, and a second one created in this sort of pocket. If I move a little bit further, one of the key to performance and reducing drag of the car is to make sure this vortex here is going to burst. So without going to too many details, you want to effectively push your front wing enough so that this sort of vortex here is getting so big that it's going to splash into sort of bits of vortices, and the energy is going to drop, and that means that the velocity in front of the tire is reduced, or the energy is reduced, and that will reduce the drag or the pressure that is applied on the tire, so the drag will reduce. This is one of the main things that you do at the beginning. You can see that this car hasn't been developed enough, and simply because it's the very beginning of the project. But we know that we need to develop this area so that this vortex will effectively get bigger and bigger until it bursts, and the drag will reduce on the car. You don't want to do that everywhere. This one doesn't need to burst. You just want to control it nicely and make sure it goes where you want. I need to close it again, sorry. Okay. I'm going to go a bit further now. You can see that the Y250 vortex is still very significant here. It's still there. What you want to make sure is that it doesn't hit your suspension, which is why the suspension legs are quite high at the front. For this reason, plus the fact that the chassis is very high. But you don't want it to sort of hit the suspension leg. You can see there is like what we call a guide vane here under the chassis, and that creates some smaller vorticity here. And this is combined with the big one, effectively a system that works together. And the reason of having these vanes is to control where the big Y250 vortex is going to go. So you want to make sure it goes in the right place further along the car. This is how we work. We are sort of moving around these vortices by adding some sort of components on the car. This is now a bit further. You can see the start of the floor under the chassis. You can see that we have rotational flow happening again. And this is the reason why we have these fences, is to strengthen this rotation here and create a bit more suction under the floor. The other advantage of a vortex is the static pressure inside the vortex is sort of very low. So it acts as like a hoover. It sort of sucks the air. So if you can locate it under the floor in the right areas, it will actually suck the air and create more mass flow under your car and make your floor work better. Interestingly, the Y250 vortex is sort of disappeared now, so it's sort of weakened. And again, it's a sign that this car is not developed enough, because normally it should travel a bit longer. This is what we call the barge board. So if I come back to my car, just to make sure we follow where we are. Okay. The barge board is here. You can see the barge board is creating a differential pressure across it. So there is a bit of pressure building up in front of it, and behind it will be the opposite. The pressure is going to drop. And if I come back to my picture, we don't see the pressure here because we're looking at velocity. But the implication of the barge board is to draw some air behind it and effectively work in conjunction of the start of the floor and make more air going under the car, same as before. You can see that we've created rotation here, which will also create some suction at the beginning of the floor. You can see these big vanes here on the sides, turning vanes. and they will help to control the flow that will go on the side. Okay, this is another picture of the car. You can see this vein that will control the flow along the side pods. Okay, and I'm going to move just further away. You can see that this is typically the way we look at the car. We just go through this sort of video, and we're taking our conclusions in terms of what's working, what is not, what could we do next in terms of development. We're closing towards the diffuser area, and one of the features in the diffuser is all these fences, vertical fences. They cannot be anything else than vertical by regulation, but you can give them the profile you want in plan view. And you can see, again, small vortices forming on the edge of them. And what you try and achieve is to make them work very well. So you want to align them to the flow and give them the sort of angle of attack they need. So they create this sort of vortices of the right magnitude. Again, big rotational flow here, purely because of the effect of having a big wing with a discontinuity, with the discontinuity of the end plates. Quickly, you can see what we call the louvers here. So the sort of openings on the side of the end plate on top of the rear wing. Everybody's got that. It's a small sort of feature on the car that sort of helps to actually reduce the drag of the car. It sort of detunes the rear wing efficiently, so it reduces the top pressure on top of the rear wing. And it works as well in conjunction of this vortex on the side here. So, you know, it obviously a lot to learn and a lot to look at, but at the same time, once you're familiar with this flow, it's just a matter of tuning it and making it a bit stronger in the right places. And this is purely what we do when we design the F1 car. Okay, I'd like to think that we might have some questions now, and I think it would be nice to answer them and carry on the presentation this way. So, Milad?
Yes, can you hear me?
Yes.
Great. So, guys, Nick, first of all, thank you very much for this this presentation. There's a lot of things which are quite new for me and very interesting. I think we will have some questions. So, everybody who has a question, please just type it into the chat. And then, yes, we can start to discuss these questions. Okay, let's see. A lot of people asked, first of all, will this record be made available for download later? Yes, guys, we will make this webinar available for you as soon as possible. I hope in the next days on YouTube. And yes, then let's start with the technical questions. First question, quite interesting. It's from Luke, and he asked, or he wants to know, Nick, why the flow is asymmetric.
Okay. Actually, the flow is symmetrical in this simulation. Just as a reminder, and I come back into ParaView. Can you see the screen, Milad? Okay. And if I remove the reflect here, I only show what comes from the simulation. We have only simulated half of the car. Okay. So we've put a wall in the center of the car that would be what we call a non-slippy wall, a slippy wall. So it's effectively simulating a symmetry of the flow. And so effectively we just create a symmetry to see these pictures, which means the flow is symmetrical in this case. We can also simulate full cars, and we've done that obviously in the past, and we actually normally do full cars most of the time when we want to simulate a steer or a car and cornering, but not in this case. Okay, Milad?
Nick, I'm back, sorry. Yeah, although a lot of questions are coming in, I hope we can answer them all in the right order. Kyle wants to know if you can show again how to set up streamlines.
Okay. Okay, so I'm going to do it again. I'm going to delete the existing one. So you need to have the case.foam selected, so you know that the streamline will come from using the complete field, which you need. You can either click on this stream tracer, which is the shortcut. You need to, if you want it from a line, you need to change it here, line source. And then you need to enter the X, Y, Z of 2 points that define the line. In our case, we wanted -1, 0, and then 0.1, so it's slightly above the ground level. And then again, -1, -1 in Y, and 0.1. And just click Apply. That's done it. Okay?
Yes, great. Maybe just general information. I think I mentioned it already, but on our, maybe Nick, you can show the site on the landing page, simscale.com/F1. We also have a post-processing tutorial for you. And if you have other questions, just send them to support to f1@simscale.com. Or I think the best way is first to try to do it on the F1 technical forum. Great. Yes, there it is. If you scroll down, Nick, you know, there is this quick guide, visualize results under resources. Exactly here, you can find some technical stuff, guys. Great. So there is the next, it's not a question, I think it's, Luke is saying an image at 258, the flow is not equal on both sides.
Oh, okay.
I've checked.
On which picture? On this picture?
On picture 0258.
Right.
Where?
This one?
I don't see any asymmetric, but maybe I'm not the best observer. It's symmetric, or isn't it?
I think it is, and I think if it's not, it's purely just a difference in the rendering or in the sort of contrast level of the picture.
Yes, because this is, Nick, as Nick mentioned, this is a half-cut simulation, and these small things are sometimes a reason of visualization. So the flow, I think, is in any case symmetric. Akrem would like to know how you start when you design a new front ring, and if you start with the main wing, the end plates, and if you use parametric design in development.
The car is designed at the moment in NX, and you can see it here actually. And I'm not gonna go into many details, but if I display the wing, the way it is designed, and you can see it here, we start from this sort of sketch. And you can see that every single element of the wing, 1, 2, 3, 4, comes from this sketch. 1, 2, 3, Okay, 1, 2, 3, 4. There's 2 behind this. Every wing element is designed in 2 dimensions in these sketches. So we effectively define what's going to be the thickness of each element. So if I come back here, okay, it's a bit more easy to understand. You can see we give sort of parameters everywhere. So every element is going to have a thickness. First one, second one, third one, fourth one. And then we just link these sort of lines to create some sort of profiles with curves. And then we go in the 3D space. Obviously, as you can see, the wing is not purely in 2 dimensions. It's got some loft. It's got some swept. It's a swept solid. So it's got a defining profile, and then it's got defining guides. You can see a guide for the trailing edge. You can see a guide for the leading edge, and each element's got this in. So that's how I design them. There's many ways to design wings, and you have to apply some sort of logic, obviously, to make sure you sort of keep the gap between each element, 1, 2, 3, 4. You can see the slot gap in between is constant along the elements, even though you've got some 3D movement into the elements. So it takes a little bit of practice, but not all the elements are 3-dimensional. These ones are purely extrude 2 dimensions. So you can start by doing 2 dimensions and go to 3 dimensions. Okay, Milad?
Yes, thank you. I think one thing Akram also wants to know which part you're starting when designing the wing, but I think it's the profiles, right?
Yeah, it starts from a profile, yes. But the profile is we design the profile. We don't take profiles from libraries. We actually design the profile from curves.
Okay, good to know. Next question about wings. Nunes Milan wants to know, how does the number of elements and the positioning helps to increase the efficiency of a wing?
Okay. First of all, if I come back to this slide here, I don't know if it's going to be easy to see it, but they used to have 2 elements to start with, purely because remember that the regulation was written in 2009, so 2010 is the 2nd year of the development in this regulation. So you always have to start simple and then complexify. So 2 elements in 2010. What happens is some areas of the wing need to have more camber and more suction, purely because you test more camber. So what I mean by more camber is you increase the load on the wing itself locally, and it's quite clear on the 2015 picture near the Y250 vortex here and there, obviously. The camber is very high because the chord of the wing is very short. So you can imagine each element is very loaded locally. If you only keep 2 elements, you cannot keep the flow attached. You're going to separate. So that's when you start to split more. So you start to have 3, 4, 5, and now 6. Well, in their case, 5. Some people have up to 6 here. And the same happens in front of the tire. There is a lot of loading going through here, not only vertically, but the wing is sort of going outboard as well. And if you keep only 2 elements, the flow is not going to stay attached. So you add more elements to keep the flow attached, because some more air is coming along the wing, if that makes sense. Okay, Milad?
Great, thank you. Joe wants to know, where does the term Y250 comes from?
Oh, it's very simple. You see the location of this, the end of this profile here. This is the FIA profile in the center. You cannot do anything about it. The FIA wants you to have this profile. And basically, the distance between the center and the end of it is 250 millimeters. And in engineering term, when we design the car, we talk about Y250 in terms of location, because in the Y direction, we go 250 millimeter, and that's where it happens. Okay?
Great. Next question is Alberto. A very good question. Wants to know if raising the nose increase the flow under the chassis to the underfloor, or does it just help to manage vortexes at this Y250 you just described?
Okay. Well, actually, interestingly, on these two pictures, obviously the height of the nose is different. This is a sort of a high nose configuration. This is a low nose configuration. The reason is the regulation has changed for the nose. If I come back to the first slides, you can see in green, you cannot go above this line. So we've designed the nose absolutely on the limit in terms of height. Everybody has it. So that's the first thing. We need to have a low nose now. If you raise the nose, what you tend to do is you actually decrease the front downforce purely because there's no such pressure pushing on the nose, obviously. And yes, you allow more flow in the center of the car under the chassis, which has got some benefits for diffuser. So it's a better quality of air going to the back of the car, but you've lost front downforce as well. So you have to see if overall it's better. I think a high nose was better overall, and if people could choose, they would probably want to go back to a higher nose. But the low nose works as well. But when you go to a low nose solution, you need to adapt the front wing a little bit, because effectively what's happening in this area is different. The Y250 vortex is different. So you just have to redevelop your front wing in that area. But you can achieve a similar result at the end, but you need to move things around a bit. Okay, Milad?
Alberto also wants to know what's about shortening the nose.
Yes. One of the problems we have this year is, again, I will use this picture. The nose has to be under this line, and it needs to have a minimum thickness by regulation, and also because you need to go to the crash test, so you cannot afford to have a very thin nose. Okay, so you can imagine that the underside of the nose is very close. You can see it here. The distance between the nose and the FIA section under it is quite small. This is actually a problem because, and you've got the pillars as well. The air going in this small section, it tends to separate because it has to go through a small sort of section, which is not good. So that's the long nose problem. Is the distance to the FIA section and the creation of this sort of small section under the nose. If you make the nose shorter, effectively what you do is you take this point and you move it back up to about here. So you don't have a nose over the FIA section anymore. You clear what I call the FIA section, we understand is this piece of front wing in the middle. So you clear the FIA section from having a nose over it. So you don't have this sort of section problem anymore. And you still have a section, but effectively a bit higher. So there's a sort of bigger mouth for the air to go under the nose. The problem with the short nose is for the crash test, obviously the distance, there's so much energy that you need to absorb from the nose in the crash test. Having a long nose is a much easier way to do it for the crash, and it will be lighter because you won't have to build the nose with so much thickness into it for the crash test. So the short nose is difficult to achieve. But to be honest, the long nose is a good aerodynamic solution as well, and you can see it on the Ferrari, it works well. I sort of had to decide between long and short, and I prefer the long at the moment because I like to think that it will make the cars lighter as well. And I think if you work the details of your front wing pillar, you can achieve a good solution anyway. Okay?
Yeah, thank you very much, Nick. Then, this is also a question about CFD, but I think you can also help there. People are asking which software or meshing method was used to mesh the simulation you just showed us. And
do you want to answer that, Milad? Or?
Yes, maybe that's better. Okay, the simulation was done on SimScale. This is, yes, online simulation platform where you can do CFD simulations, for example, web-based, cloud-based, and there you can also I think I mentioned it 2 or 3 times already, but there you can also access all the simulations and analyze them yourself. And meshing was done with SnappyXmesh as well as the solving with OpenFOAM. This is both open source software, which is also used in F1. I'm not sure, but I think quite sure that Sauber is using, for example, also OpenFOAM. And yes, that's the software which was used. Next question is by Zhang. If it's not, or he asks, don't we need to use the transient characteristics?
So I guess the question refers to the CFD methodology. Or what is the question referring to? I mean, you can do CFD effectively like we did here, which is not transient in the sense that it's called runs. So it's an average method. So it doesn't know about the particles moving with time. It sort of finds a stable state of the flow around the car just through iterations. But we can also do CFD transient called DES, D-E-S. And we've done this as well in the past. The simulations take longer, but they can give you a slightly more realistic results because it's like having a flow effectively moving at the, through time along the car, so you can see the transient effect. So behind the tires, for example, you can see turbulence moving left to right and things like that. But the steady state method, which is what we use because it's much faster to compute, is very close in terms of results. So to develop the car and do a lot of simulations, we like to use the steady state methodology. Okay?
Okay, great. So we have so many questions that we're running out of time. I hope we can answer them all, Nick. I don't know what are your plans for today. We will try our best, and in the worst case, we will answer this question on our blog. But let's try to do this all. Okay. A question is, in order to reduce the drag force, you should create a vortex before the tires. I think this is a question by Thiago. So, Nick, will it make sense to create a vortex before the tires for reducing the drag?
Yeah, and I think I mentioned it. I can show it again, and we are doing it effectively. It's really hard to do. If I come back here, that picture shows the rear tire. You can't really do it in front of the rear tire significantly because there's no geometry. The bodywork is very far away. You just have the floor here, but you can't do much. But for the front tire, you can, and that's what we do with the front wing, which is, I'm coming back to it. Okay. So this is the end plate of the front wing, and this is one vortex. This is another one, quite a big one. Not as big as it should be because, again, we need to develop the geometry further by steps. But the aim is that this becomes big enough that it starts to reduce the pressure pushing on the front tire. And if I come back here, this is what we're talking about. This red zone is effectively creating drag on the car. You can see on the lower part, it's not as strong because we have this vortex effect. But we can make it even less of a, we can even reduce even more the pressure by making the vortex stronger. So yes, we do use it.
Okay. Yes, I think that is a good answer for the question. Then, sorry, I have to look because there's so many questions. This is a question by Ido, and he wants to know how internal components are modeled, like engine cover or flow under the engine cover and the side pods and the exhaust, and if this has any effects on mesh quantity and computing time. Yes, Nick.
Yeah, well, quickly, that this very simulation we are looking at doesn't have an internal flow. You can see I'm looking at effectively behind or inside the car. Normally some flow would come in through here, but we've blocked the inlet and then go out here, but we've blocked the outlet. Simply because we wanted to save some mesh size, wanted to make the model a bit more simple so that it's much easier for you to download and play with it. But when we would develop the car, we would actually simulate all the internal flow. You will even have the flow coming inside the engine. So there will be some sort of suction effect. So some flow will come in the inlet and will go out from the exhaust air. And some flow will come in this big inlet through the radiator out. And I can show you quickly in CAD, coming back to the main model. Okay. The main model is having a radiator. So if I slice the car, okay, you can see that, and that's very easy to do in CFD, and we will do it further on the SimScale platform because this makes the simulation much more realistic as well. But the flow will come in, go through the radiator, that will effectively, it will simulate a pressure drop, so the air is going to be slowed down through the radiator, and then go in the engine bay. You see the engine here, and then come out there. There will be some flow coming out through the exhaust. So yes, we can simulate the internal flow, and we will. We have to do it to develop the car anyway. Okay.
Yeah, so I can confirm it's possible to do porous media and stuff like that on the SimScale platform. Maybe just for information, the reason why we decided not to do that is that we wanted to really to keep the simulation as small as possible and really focus on the most important things. And if we had the internal flow also there, a lot of you maybe had not enough resources on the local computer for visualization. So that's the reason. But it's technically possible. In the future, we will also release some library projects of the Perrin F1 car, including all porous media and stuff like that. Okay, then the next question is by Inko, and Inko wants to know that, or you mentioned, Nick, that the vortex did not go along the car and towards to the rear. And you said that the model is not enough developed. And Inko would like to know if you what are the details, and can you maybe explain this a bit more?
Yes. Okay, there's one thing that, so I'm coming back to the picture that explains it. Okay. Okay. So this is our front wing. Okay, front wing creation of the Y250 vortex, and then moving along the car. It's still there. We can see it there. Going further up, it's not there anymore. So it sort of stopped, and actually you can see it went up at the end. It's quite weak, so it will be dragged a bit, and it's sort of hitting actually the suspension leg at the back. Believe me, on a developed car, it doesn't work this way. It stays in this area much stronger. So what I mean by that is, at the moment, we've only done about 10 iterations on the car. So we have designed the car based on experience, and then we just do one change at a time, trying to improve. And it's very clear that we need to develop the front wing much more to make this vortex stronger. It will mean that we need to crank or put more camber on the front wing in this area. So if I come back to my Mercedes comparison, it would mean that we need to do what they've done, which is put a lot of camber here, but that means making sure the flow is still attached, so maybe more elements, the same discussion, and that will mean the vortex will be much stronger and travel longer. And actually, we know that the vortex needs to be going at least up to the beginning of the floor. So if I come back to this picture here, we said, right, okay, at the moment the vortex starts here, goes there, and stops about there. But in reality, it will go a bit outboard, pushed away by the car, and go outside of this vein up to there. The other thing on this simulation is the car is a little bit high in terms of ride height, which means also the front wing is not performing as much as it will on the racetrack. We just need to lower the car a bit, and that will make the whole vortex much stronger as well. So it's all part of the process of just developing the geometry of the car, knowing what we want to do, and we have some, obviously some targets. The Y250 vortex being stronger is one. And then play with the attitude of the car and just carry on like this. But you know, if we talk again in the future when the car is developed, it will be interesting to see how how these things have moved on. Okay, Milad?
Okay. Okay, that's a question I can answer. Alan asked, why did you set for boundary conditions inlet, front of the car, and outlet behind the car? Yes, Alan. I think you've checked out the simulation, and the reason is that you want the flow to come in before the car, you know, and in the wind tunnel, also the inlet would be before the car and the outlet behind the car. And in the end, inlet just means that, you know, flow is going in. So you have a fixed velocity. In this case, I think it's 60 meters per second. And outlet means that the velocity is not fixed, but the pressure, that's the atmospheric pressure. And that's the reason why we set up like this. And we know it's not very, very easy to understand this from the beginning. That's the reason why it's ready to run simulations. But we have also a lot of tutorials and other stuff on SimScale, which you can access for free and to learn more about simulation and CFD in general. Then the next question is from a student, from Sergio. And Sergio would like to become an aerodynamic engineer in F1 or LMP1. And wants to know if you would recommend him. I think he just graduated, to apply for a PhD, or is that not really necessary?
I didn't do a PhD myself, so it's easy for me to say that it's not necessary. I don't know if there is one way to achieve, you know, being an aerodynamicist in the industry. So I don't have a strong opinion on it. I guess it depends on, you know, how far you want to go in studying and going into certain details and into the theory, and or when you're ready to go and start, and also when do you have the opportunity to find a job in the industry, in Formula One if you want to be as well. And then you learn a lot anyway from being inside the industry. Formula One is actually a great school itself, because it gives you so many tools, state-of-the-art tools to not only to learn, obviously, to do your work, but by doing your work, you actually learn and study a lot, because every day is about learning something on the car. I hope this answers the question.
Yes, I think that this was a good answer. Then the next question, although a lot of questions regarding the simulation itself, please guys, if you have questions like which turbulence model was used or what are the boundary conditions, this is very specific, and the easiest way is to just check out the simulation. A more general question is by Filippo. He asks, why is the drag effect reduced after splitting the big vortex at the front wing? In many tiny vortexes impacting the wheel? Thank you very much.
Okay. Well, vortex mechanism can be a bit complex, but very simply, the vortex can have different states. It can be strong, and the core can be small with a lot of suction in the middle, or it can burst, and it's like breaking up and splashing. That will be at the end of its life, if you want. So the actual pressure that the vortex will apply on the tire when it hits it depends on the state of the vortex. If it's very strong, it won't necessarily reduce the pressure on the tire very much. If it bursts, then it will reduce the pressure. So we're talking something very difficult to adjust. Actually, if I show you it here, it's we're under the car, and this big tunnel here. This is where we're trying to create this vortex and make it travel and go and hit the tire here. Along the life of this vortex, from beginning here at this edge to the end when it hits the tire, depending on how strong you make it, it will have a different state. It will burst or not burst, and that will change the pressure it pushes the tire and the drag on the car. So this is how it works. It's one of the most difficult things to develop and study in Formula One, because you might have the state of the vortex might change a little bit if you look at it in CFD or in the wind tunnel or even on the racetrack. So, it will be really interesting to talk more about this in details later when we develop the front wing. Okay?
Some people ask how close the CFD simulation results are to wind tunnel test results.
I like to say, remember that CFD is a model, wind tunnel is a model, and actually wind tunnel can be different from the track as well, because wind tunnel is a model. So it's always a bit different. It can be very close. It depends on which car you study and what is the attitude of the car as well. But there is one thing for sure, is the CFD modeling is getting better and better. For one very simple reason, is we can split the model in much more cells now because of computing power going up. So before you would say, okay, we can do only 1 million cell. Now we can do 100 million cell. And that will always improve the accuracy of the model. And we know that it will only increase and improve. But to say how close it is from the wind tunnel, it depends. It's a case by case. It is on average, it is very good, I have to say.
Okay, good to know. And Junaid wants to know if dynamic pressure is as important as static pressure for you, for your result evaluation.
Both are very important. You want to look at both. The static pressure is really the result. It is the pressure that is applied on the surface of the car. So this is the consequence of everything. Okay. What is the static pressure that's creating the downforce? So this is like the result, and you sum the pressure and you get the force on the car. But to create that static pressure, you need to understand what total pressure you have around the car. You know, what flow, energy, what velocity is going around. So you need to look at the total pressure. And there is a link between the two, obviously. You know, we talked about Bernoulli, we talked about velocity increasing under the wing and pressure, static pressure dropping. So that link exists. So you need to look at both. And I have to say, this is the key to everything. This is the key to understanding how to improve the design and just know what next step you want to take on the design. So look at both. Dynamic pressure, you have to look at it in the field, in the flow, okay? Static pressure on the car surface. This is normally how we look at it.
Okay, good to know. Then we have so many more questions. I think we should not accept any more news questions. It's too much. But one guy who has a very general question is Aspen. And he says that he has not the best technical background. And he's had not studied physics or aerodynamics. And what would be the best way or the best place to get a good introduction to F1 aerodynamics or aerodynamics in general?
Well, you are in the best place. No, I mean you know, Formula One is Formula One aerodynamics and Formula One in general is quite closed. You know, obviously they are not sharing a lot of information because they are competing with each other, and this is the way they want to do it. So it's not always easy to find the information. You can find a lot of maybe books or documents that will explain some general things, but this will be more or less the same as what you can read for aerodynamics around the aircraft or any sort of vehicles. But for Formula One specifically, I think obviously this is what we're trying to create here, is also the possibility to talk about, you know, hands-on current design, actually evolving the design in front of you guys, and try to just talk about what's happening in the flow and learn from it. And I think this is probably a good way to learn, because this is also more fun, because it's like playing with the design and seeing things happening. But apart from that, I don't really know, I have to say, apart from going and work in the industry. Okay.
Okay. Next question is how the car is optimized for crosswings, and but I think this is a question I may answer, because he asked, Manje asked Nick and the SimScale team. You can also simulate crosswing configuration for the car. It's quite easy. You just you know, change the angle of the car to the wind tunnel box, and then it's working. Or correct me if I'm wrong, Nick.
No, exactly. And crosswind optimization is something very important. You know, the car is not always in line with the wind on a racetrack, and actually in corners it's never aligned with the winds. It's always at an angle, because the car is you know, is sliding on its tires. So you can have angles up to 10 degrees, or but typically 5, say, between the wind and the car. So it's important to look at the car at crosswind angles. It's very important. And this is definitely something we are doing as well as part of the development of the car. And CFD is a very good tool for that. But you need to simulate the complete car, obviously, in this case. And one thing, you know, that's we're having all these questions. It's really nice, I have to say. But I encourage people to try and run the simulation themselves if you want to test something, or even crosswind, for example. You can probably test it and get new questions ready. We have a new workshop in 1 week and then another one in 2 weeks, so it would be easy to follow up new questions.
That sounds great, Nick. Okay, so we have reached the end of the webinar, but I think we can still make some questions. Okay, let me just look through the questions, which one is asked maybe more than one time. Oh, this one I think is quite good. Ethan wants to know how you start to design the car.
Right. Well, the first thing, as I said, is the rule book. You need to understand what you can do and what you cannot. Without starting to go into the CAD system and doing complicated surfaces or all this, you need to sort of draw the boxes that I've got here. Sorry, this one. And then you can see where you can design the car. And then after that, you have to split things. You have to start with maybe the chassis or the front wing, do one thing at a time. When it's too complicated, it means you are looking at too big a component or an area. So you just split it in components, in smaller parts. And then you put it together. If you look at aerodynamics on an F1 car, you wouldn't simulate the front wing only or the rear wing only. You need a complete car because it doesn't make sense to optimize the front wing if you don't have a car behind it, or the rear wing if you don't have the car in front of it. But it means that you have to put all the blocks together. But as for what to know to do for designing the car, it's from experience. But keep things simple. I like to keep things simple. You can always spend a lot more time to surface, do complex surfaces later. You can start with a more simplified sort of boxy looking car and then put it in CFD and see what happens. But I know an F1 car is not the most simple thing to design, and that's why also we're providing the open source design, because it makes it much easier for everyone to actually work on a prepared starting point. In a way, we have a starting point for you to look at and maybe try your own solutions. Yeah, so there's no simple answer to it, but we're trying to help it this way. Okay. Okay, Milad.
Sorry, I was still muted. I think let's do 3 more questions. And there are so many more questions, but we really cannot answer them all. But we will make a blog article about the question which we could not answer right now. And next time, maybe I will talk to Nick that we have maybe some more time for answering your questions. But a lot of questions, I think, also you can discuss on the forum. It's something you can help each other. And maybe, Nick, if you have time, you can also answer some questions in this forum directly. Let's see. Then a question or something a lot of people are asking is if this word vortex are only important in F1 or also for street cars.
Oh, for street cars. Well, first of all, you have vortex. You have a vortex when you have a discontinuity. By that I mean that if you look at an airplane, there's always a vortex at the tip of the wing. So purely because the wing stops, that is a discontinuity, and it starts to create a vortex at the tip. In Formula One, you have a lot of discontinuities, which is why you've got vorticity. I mean, I come back to the main one, the Y250. It's very simple to see that you go from this profile to a very loaded profile here, so that will create a vortex end of the wing. So you've got a lot of rotational flow happening here. On a road car, it's pretty much a very simple body with no discontinuity. It's like it's like a big box. So you don't have as much vorticity happening. And if it happens, it's not really studied anyway as much. So no, it's to answer the question, it's much, much less, or if not at all, studied for road cars. Okay, Milad?
Bruno wants to know, or he noticed that the diffuser starts about the middle of the rear tire, and he wants to know if that's a regulation thing or is it your design choice?
Yeah, it is the regulation, definitely. As you can see, the diffuser starts here, on this fillet here. You know, we would all love to have the diffuser starting there. That would make the car much faster, but no, we can't. So the diffuser starts there, and in terms of height, maximum is here. So this is by regulation, yes. Yes. Okay, Milad?
Thank you very much. Sorry guys, but I think really time has come to stop this webinar or our first session today. There are so many more questions. We'll answer them later on. And yes, first of all, Nick, thank you very, very much for your time, which was really great to have you here. And I'm really looking forward to the next 2 weeks where we'll have you as a speaker also the same day, the same time. And yes, next week we'll about driving the slipstream. So maybe Nick, you can give us a short preview what will be the topics of the next webinar.
Yeah, thanks, Milad. It's been really nice, and same. Looking forward to the next. Driving in the slipstream, we'll look at putting two cars behind each other in the CFD process and see what the effect of the first car has on the second one. And I think we'll still come back to the basics as well, like today, and answer more questions, because this is, I guess, this is a nice way for everyone to get a bit more into it. So I'd like to say thanks to everyone. I'd like to invite people to come on Perrin.com as well, if you want to have a bit more information about our projects, and there is some more information as well available there, and you can be in touch with me this way as well. So thanks everyone, and speak next week.
Thank you very much, guys. See you next week. And if you have any questions or problems, just send a mail to f1@simscale.com. Have a nice weekend. Bye.